Hello everyone, welcome back. I hope you guys had a great weekend. Previously we had Alex and Jin give us an overview of the circuits and the smart contracts. Today we have Alex from the Summa team going over the code base of Summa's prover. Yeah, over to you, Alex.
Hi everyone, this is Alex. Let's briefly review what we have learned in the previous sessions about Summa architecture and specifically the part that applies to the prover. So as we may remember, the prover needs to interpolate the user balances into a polynomial and commit to that polynomial and then provide a few opening proofs for everyone to verify the necessary information about the state of exchange's liabilities. So here I want to ask you a brief question just to make sure that we're all on the same page here. So why does the prover need to publish a KZG opening proof at x equals 0?
That
Feel
would be
free
the
to
grand
speak
sum,
or
right?
just yeah, that's correct. That's correct. Because this is the grand sum proof. Effectively, it's not directly a grand sum proof. It's proof of the constant coefficient of the polynomial that is located exactly at x equals 0. But we remember that by multiplying that constant coefficient with the number of users, we obtain the actual grand total sum of the polynomial evaluations at the roots of unity, where all our user balances are located. And of course, probably no one has any questions. What are the user inclusion proofs? And they are located at the specific user designated points that are on the roots of unity. To briefly review what the circuit does under the hood, let's remember that the advice columns of the circuit are interpolated as polynomials inside the Halo2. So we don't need to do any extra action here to apply the Lagrange interpolation. And also another nice feature of Halo2 is that it also creates the KZG commitments to those advice polynomials for us. So we don't need to do any extra action to create the commitments. And of course, here we're talking about specifically about KZG, which means that we're using the PSE Halo2 fork where there is a feature of KZG commitments instead of an IPA. And this leads us to the circuit structure, also from the previous session. Let's quickly recap. So in the circuit, we have the balanced polynomials for n currencies, as we support not just one, but an arbitrary number of currencies. For each of the balances, we need to do a range check. And also we need the user ID polynomial. And here maybe one more quick question to the audience. Why do we need that user ID polynomial here?
So that you don't use, so that each user is provably unique, right?
Yes, so that when the user receives a proof, which looks like an evaluation of a balanced polynomial, at some point, the user can make sure that the user ID polynomial proof is also evaluated at the same point in terms of, at the same value of x. So, which means that even if someone else happens to have the same balance as you, you can be sure that the exchange couldn't cheat by providing the same balance opening to two different users and including just one of them into the polynomial. So this way we're sure that there is a unique correspondence between the proofs and the user, and no proofs can be reused for different users. And on the right, in a different color, we can see a fixed column here, which we need for the range check chips, and they all share the
By the way,
same
Alex,
fixed
sorry,
column. Oh yeah,
Alex, I don't know if you think you
yeah.
are sharing something, but you are not actually. I don't see anything.
Oh my God, why no one told me about that? Okay, I know we can start over probably, or yeah, I totally forgot to start sharing. So guys, next time, please just tell me right away so we don't waste time. Okay. Okay.
Okay, you can just
Hi,
skim
everyone. Yeah, let's
quickly through what
skim through the slides. Yeah. So here we have a brief recap of what the prover does on the prover side. And here we have we have a very useful diagram that reminds us of what Halo 2 is doing for us. And we don't have to interpolate the polynomials manually, and we don't have to commit to those polynomials manually, because we only need to run the prover, and the prover will do all the work for us inside Halo 2. And here we have the circuit structure that we'll later see in the code. Yeah, and besides all the advice assignments, the fixed column is assigned with constant values, just to remind that these constant values are necessary for all the range check chips, because the range check chips are checking that the decomposition of every balance, every 2 bytes of the decomposition belong to the fixed column. So it's a valid value that is allowed. So let's get to the code. Today we'll go through the code a lot. And please tell me if the code is like big enough. I may have to zoom in for it to be visible better. So we have in the tests, we have an integration test that pretty much sums up the prover workflow, but also it includes the verifier side. But here we can see all the logic that the prover needs to perform as well. And we'll go deeper into that code step by step. So let's get back to the presentation. And first, let's talk about what's happening in the circuit and how does the circuit reflect the diagram that we have seen earlier. And maybe we can switch between the circuit and the diagram a couple of times just to establish that correspondence. So during the circuit configuration, the prover needs to allocate the necessary columns. As we know from the diagram, we need one advice column for the user IDs, then a number of advice columns for the currency balances, and the corresponding number of range check chips that, of course, require a certain number of advice columns. And then we only need one fixed column to fill it with values for the range check. So as we can see here, we are allocating a username column, then we allocate n balance columns that are actually unblinded advice columns, as opposed to the regular advice column for the username. And here maybe also a good time to ask you a question. Why do we need the balance columns to be unblinded?
We don't need the random values and the total isn't affected. Like the whole
Yes,
thing
that's
we have.
that's
Yeah.
correct. That's correct, because if we were using a regular advice column, then it would be filled with some random values beyond the useful values that we put there. And it is done to improve the zero knowledge inside the Halo 2. But in our case, those values would interfere with the grand sum of the polynomial evaluations. Then after that, we can see that we are allocating that fixed column that we will fill with all possible 16-bit values. And we are instantiating the range check chips. And to configure them, we also allocate the necessary number of advice columns. And in our case, there are 4 advice columns for each range check chip, because we are operating with 8-byte balances. So we are checking that every decomposition belongs to a 2-byte table. So we are dividing 8 by 2, and that's why we need 4 columns for every range check chip. And that's it for the circuit configuration. The next phase for the prover is the circuit synthesis. So let's take a look at the synthesis phase. And also side by side with the diagram, just to remember what's going on. The synthesis phase is very simple here compared to a typical, let's say, typical ZK circuit that you may see in the wild. Again,
Can you
because
zoom in,
we're not doing,
Alex?
oh yeah, sure, yeah. Let's zoom in a little bit and go line by line. So first of all, we are constructing the ZK, the range check chips, and we fill that fixed column with the actual values, where we're just going from 0 to the maximum of 16 bits. This is the fixed column here. And this fixed column is shared among all the range check chips. Then we're filling the actual decompositions of the balances into the range check chips. So as you may remember from Summa v1, each range check chip here contains a decomposition of each balance, each corresponding balance into 4 bytes, and the value of every 4 byte of every 2 bytes should belong to the fixed column. So here we are actually performing the decomposition and assigning the values and performing the necessary constraints. And somewhere here got lost the actual assignment of the balances, which is a very, like, let's say, very quick operation here. Let's find it. A little bit difficult to find it with zoomed in. Zoom out a little bit. Size.
Is it
Yeah,
117?
actually it's the balances are already assigned here. We are passing the assigned cells inside because because there is a separate function to assign the entries that is shared between two different configurations of the circuit. And here, what it does is very basic. We are simply putting the balance values inside the Halo2 circuit, inside the table, to the corresponding columns of the corresponding advice columns. So the circuit part is done. There is nothing else left to do in the circuit. And we can continue to the actual workflow of the prover. And maybe if someone has any questions, I can answer them now. Okay, let's continue.
So far, so good.
Yeah. So what happens inside the Halo2 prover after we assign all the values? Probably that part can be quite interesting to many of you, since we're leaving it out and we actually, we're probably not going to modify any code there. Then just let's have a look at how it works under the hood. So now we are inside the Halo2 prover. And this is a very, very big function. If you go and take a look, you will see that it's like hundreds of lines of code. And we are only interested for today's presentation, of course, we're only interested in a couple of places in that code. And the first one of them is how the KZG commitments to the polynomials are generated. So here we can see that the commitments are done in the Lagrange representation of the polynomial, which is very convenient probably for Halo2, because you can do it even before evaluating the actual coefficients of the polynomials. But then later, the KZG still works in the same way as the normal KZG. And the second part that is interesting is the actual interpolation of the polynomials. And here we can see that the advice polynomials are transformed from the evaluation form, which is synonymical to the Lagrange form, into the coefficient form, where the actual Lagrange interpolation is happening. And we have reviewed that formula in the previous session on Summa v2. So now let's go to the end of this function, of a very, very long function, and let's check again how we are returning not just the proof transcript in a tuple from here, but also the advice polynomials. We need those advice polynomials later outside of the proof, because we will need to generate the opening proofs. So now let's return to the prover workflow. And let's take a look at how what the prover does next after generating the zero knowledge proof. So here we can see that after the prover has instantiated the circuit and generated the zero knowledge proof, the prover obtains transcript of the proof that contains the KZG commitments inside. As we can remember from this simple diagram here, that the transcript generated by Halo2 contains the KZG commitments that we need, and also the prover obtains the advice columns from the in the form of advice polynomials, of course, that we can see here. What the prover does next is opening the grand sums. It's exactly the opening of KZG commitments to the polynomials at x equals 0. So if we try to go inside this function, then okay, we go to utils and we go to open grand sums. We go inside this function, then we can see that the prover is creating the opening KZG proofs at a specific challenge that in this case is equal to 0. This is the field element that is equal to 0. And as we said earlier, this is necessary because here we are proving the constant coefficient of the polynomial, and it is located exactly at x equal to 0. So after the prover is done with that, sorry, I think I closed the necessary tab. Oh no, it wasn't this one. So we're going back to our prover logic. So after the prover has generated the grand sum openings, the last thing that the prover needs to do, and anyone who is verifying those proofs, is to actually convert the constant coefficient into the actual value of the grand total. And as we remember, we need to multiply the constant coefficient of the polynomial by the number of users. Or we can do the opposite here. When we're verifying the opening proofs, we take the expected total amount that the prover, of course, knows, because the prover is the exchange and the prover knows the total sum of all the balances for every cryptocurrency or included in the liabilities. So for the opening proof, the prover needs to divide this total sum by the number of users, which is the same as the length of the polynomial in the evaluation form here. Because we don't have directly have the division operation in the prime field, then we are calculating the inverse element of this number by which we want to divide. And we're multiplying the total of this currency by the inverted size of the polynomial here. And of course, here, when I say that the size of the polynomial is the same as the number of users, I assume that the prover managed to fill the polynomial with the user balances. But as we know from that mathematical technique that we're using here, the polynomial can also contain any number of zeros, and the grand total of the polynomial will still be calculated correctly. So that's why here we need to divide or multiply by the number of actual points in the polynomial, even though some of them can be zero. And then what the custodian needs to do later is to create the actual proofs for the user inclusion. And here we fix, we were doing it on the example of some user who happens to be user number 4, and with zero-based indexing, this will give us the index number 3. And here we can see that we are opening the KZG proof at a point specific to this user. And if we go and check what this function does, we will see that the function is very similar to opening the grand sum, because essentially it is doing the same thing. It is just creating a KZG opening. The only difference here that is expected is that the challenge point for the user opening should be specific to this particular user. And here we take our user index and raise our omega to that user, to the power of the user index. And we can see that the function that we're calling later is totally the same as the one that we are using to open the grand sum of the polynomial. The only difference here is the challenge. So this is the last thing that the prover needs to do on their side. The following is just the verification by the users. So the users receive the public proof of the constant coefficient of the balanced polynomials, and also every user individually receives the private proof of their inclusion into the advice polynomials, including the inclusion into the username polynomial, not only balances, but also the usernames. So here we can briefly stop for any questions.
Alex, is the number of users which you are inferring from the size of the polynomial, is it something committed to? Is it something, can the prover actually change the code and put something different there?
Yeah, that's a
still
great
get
question.
output?
And yeah, we had to solve this problem ourselves because we were also concerned with that. Indeed, if we imagine that there is no way to see the actual size of the polynomial on the verifier side, because verifier is operating with just a KZG commitments and their proofs, then how do we make sure that actually there were enough users, at least as many as the user base size of the exchange? And the answer here, we can take a quick detour to the previous session that was led by Jin about smart contracts. The answer is that in this version of Summa, to the contrary of V1, the verification key of the verifying key of the verifier is deployed separately from the verifier code itself. And the verifier key is laid out in such a nice way here in assembly that you can actually see the K, which is the size of the circuit. And this is the same K as the size of the logarithmic size of the polynomials of all the advice polynomials in the circuit. So we may remember that when we're proving when we're instantiating the circuit, we provide this K value. I want to go to the code, but I hope everyone remembers, because this is that K that everyone needs to set up for any Halo 2 circuit. And here we can see that the K for this instantiation of Summa, for this deployment of Summa, the K is equal to 11, which means that the polynomial size is 2 to the 11th, and we can be sure that all the polynomials have that size here. So if we go back to, like, if we think about the circuit, then we know that all the polynomials here have the length of 2 to the 11th, thanks to the verifying key that is exposed explicitly for us. And we know actually that the verifier, the snark verifier here, is actually using the verifying key. So there is, maybe I will not be able to find it quickly, but yeah, BK, here it is. So we can observe while verifying the proof, we can observe that the verifier is actually using that verifying key with this hard-coded size of the circuit. Any other questions?
So the whole proving and opening part of the polynomials you explained earlier, is it just for like one chunk? Because for huge number of users, you said we're gonna do it in chunks. So is it like the process for just one chunk, or how does that work?
Oh, that's a great question, and I was actually planning to do the chunking in the end. So that was the next part of the presentation, actually. So we will proceed with chunks in a moment if there are
Okay.
no other questions.
Okay. So this is the thing we saw right now. That's not for the chunked approach. Yeah.
Yeah, yeah.
Yeah.
Here
Okay.
we haven't seen any kind of chunking. It was just a very basic example,
hmm
as if we were just operating with one polynomial and we could fit entire user base in one circuit.
Okay. Yeah.
So I guess we can proceed and take a look at the chunking. So here, this is an example file, and it just illustrates a potential workflow for chunking. In the beginning, we are doing the same thing as we would do in a normal case. We are just parsing our user base and preparing the balance entries. And then we are splitting the user base into two equal chunks. Like here for this specific example, probably everything, of course, is even. Yeah, we have 64 user initial data, and we're splitting it in two pieces. So they will be of 32 users each. And we are calculating two totals for those two pieces. this is a quick, this was a quick testing. That's why here we're not using a range check, which is, of course, in production, you would use the normal config with the range checks. But here, just as a proof of concept of chunking, we were mostly interested in just checking the homomorphism of the KZG. So what we're doing next is we are instantiating 2 circuits for every chunk. And we are accordingly filling the circuits with the entries from the first chunk and from the second chunk. So we get 2 instantiations of the same Summa circuit that has this structure. The only difference between them is that for each of the instantiations, we're only filling them with the corresponding 32 user balances from either the first chunk or the second chunk. Next step, what we're doing is we are running the prover for both chunks separately, and this gives us 2 different proof transcripts with different sets of KZG commitments. And of course, we are also obtaining the interpolated polynomials that we will later need to prove the user inclusion. So we are extracting the polynomials from all the advice polynomials. We are just taking polynomials, for example, for a specific balance for the specific currency. Here, balance index is just 1. It's just cryptocurrency number 1 in the balance sheet. And let's take a look what we're gonna do with those 2 polynomials that were once a whole, but now they are 2 parts of that whole. So first of all, what we do is we extract those KZG commitments from the transcripts. So we are converting the proof back into the transcript representation. It's merely a matter of representing the same kind of information using some Rust APIs. Here we're not really changing anything. It's just the same proof, just more convenient for us to extract the points. And here we know the structure of the transcript because the structure of the transcript is entirely defined by our circuit. So we can be sure that, for example, the first point that is committed into the transcript will be the balance user ID point, and the second point will be the first cryptocurrency balance, and the third will be the second balance, and so on and so forth. So here we know exactly where to get our point of interest, which is the balance commitment for the specific balance index. So we are extracting those 2 KZG commitments from 2 different transcripts of 2 different proofs. And here, since these are on elliptic curve points, we are adding them homomorphically by taking advantage of the homomorphism of the KZG commitments. So after we add those 2 KZG commitments, we can use the result also to generate any kind of KZG proofs about the polynomial that is a sum of 2 polynomials. And here we, of course, are interested in generating the opening proof for the grand total of this resulting polynomial. That could, I mean, we are not operating on the polynomials here. We're not adding them, but as we know from the KZG homomorphism that if we actually interpolated a polynomial that is the whole, like the big polynomial that is that interpolates both of the chunks together, then the commitments to that polynomial would be identical to the sum of the commitments to the chunks. And I believe that here we are even testing this. Yes. So here we are still testing this. We are interpolating let's call it like a big polynomial where we are zipping two of the chunks together, and the commitment to this interpolated big polynomial is the same as the sum of two separate KZG commitments. And finally, in the end, we are opening the resulting KZG commitment at the zero challenge again to get the constant coefficient of this polynomial. And we are checking that the value of that constant coefficient is, oh wait, this is a negative test, but the test here is for this total. Oh yeah, here it is. The evaluation of the expected evaluation of the grand total is here. Again, we're doing the same thing. We know that the constant coefficient should be equal to the grand total sum of all the balances divided by the size of the polynomial. So we need to invert that prime field element and multiply the total of the balances by that inverted element. And then we see that the proof checks out successfully with the expected evaluation. As for the user inclusion proofs, this is not demonstrated in this example because the workflow would be totally the same as the workflow that we have seen previously in the tests. The only difference will be that we are proving a user's inclusion into individual chunks. Specifically here, we can imagine that we have two separate polynomials for two separate chunks. And if you, as a user of the exchange, happen to belong to the second polynomial, then the exchange will give you this information. Of course, the exchange will give you only the KZG commitments and your user index, but also the exchange will communicate to you that, and you will be able to see that by seeing what KZG commitment the exchange has provided, because all of these KZG commitments from the proofs for individual chunks, they will be publicly exposed by the exchange, of course. And you will see if for your inclusion proof, you have received a set of KZG commitment from this chunk, then it means that you belong to this chunk. And you successfully verify your inclusion into the chunk, and then later you may also check that when let's say in our implementation, when the exchange has submitted the proofs, the snark proofs for the chunks into the smart contract, it could also successfully verify the opening proof for the grand total, because the operations required to verify the proof of the grand total for the chunked approach are actually quite easy to perform inside the smart contract. I'm a little bit lost. I can't find the place where we're summing both. Yeah, here it is. So as you can imagine, what we need to do in the smart contract is to verify the KZG opening for the grand total sum, we simply need to produce the resulting commitment by summing up the individual KZG commitments for the chunks. And this operation is not very difficult to perform in Solidity. And in fact, the existing provers for both Snark and the KZG commitment, they are already performing some of that elliptic curve arithmetic inside. So by using the same kind of elliptic curve arithmetic, we are just computing this resulting KZG commitment that we can use to verify the KZG proofs in the same way as we do for the user inclusion. And I think that's it. This concludes the chunks approach.
Alex, I have a question. So, can the sum overflow? So we're summing up two KZG commitments. Is there a chance of the sum getting overflowed?
I believe there is no such a chance because here we're operating on the elliptic curve points. So we are not actually, we can't really talk about an overflow here since it's an elliptic curve arithmetic. We're not converting from like rational numbers into the elliptic curve. So we're not losing, there is no risk of overflow here.
Okay.
Yeah, it may look like this is a simple plus, but this is thanks to the Rust syntax where you can just overload the operator and the operator looks in the same way as it looks for like normal addition of some, I don't know, like unsigned integers or something. But in fact, what it does under the hood is it invokes the assigned function of the implementation of the prime field element to add to prime, elliptic curve point to actually add these two elliptic curve points together.
That is interesting. Yeah. Okay. Can you like show us the code where it's done?
Let's try. It may lead us somewhere like very far from here, but I hope that I will be able to find it's either here, it's either in the field or the specific implementation of the curve. So we need to go to the Halo2 proofs, and here we're using our own fork, and it's the same code as yeah, here this is inside Halo2. So inside Halo2 proofs, we need to go to arithmetic field, or no. So we need the curve, right? We don't need the field. We probably need to go to Halo2 curves, BN256, right? So we try to go there. Okay, it's not here. Where is it? Halo2 proofs. Halo2 curves. You have a hint for me? Go ahead, because I'm a little bit lost. Not sure that I'll be able to find it quickly here. So if someone's remember where it is.
Isn't there like a different repository by the name Halo2
Yeah,
Curves?
yes, it probably it is, and then means that this is, of course, we are not forking that, and we're not changing that. So it should be. I'm not sure if, yeah, probably PSC has this fork as well. Two. Two curves. Yes, here it is. To be honest, I haven't really taken a look into the curve implementation to find how the addition is implemented. But probably actually addition is coming from some trait. So maybe it could be a nice homework task for the fellows. Well, I guess this is a negation. This is a multiplication here.
Right above negation, I think there was addition.
Oh yeah, here it is. Yeah, also. Yeah, so I
Yeah.
guess here, yeah, you can find all the implementations. Where the operator overload is happening, I guess it should be happening somewhere in the trait. So I'm not sure where to find it now, but I guess, as I said, it can be a nice homework for you to find it. But thanks to everyone who have implemented that. We can simply rely on that implementation, and this is definitely not a place where Summa needs to modify any code.
Yeah. Um,
Any more questions? Oh, there were a couple of questions earlier. But I think I have. Yeah, I tried to zoom in, but yeah, if I hope it was visible enough. But don't worry, the slides will basically contain the links to the places in the code that we have browsed through, because of course I cannot just put all that code into the slides.
got it.
So you
I
will be
had I
able
had
to
one
study.
last question, Alex.
Mm-hmm.
I think we multiply field numbers somewhere, and we do have we find like an inverse of a polynomial using this method, this invert method, because we have to perform division there. Can you jump to the code?
Yes, let's find it. This is where, when we are opening the KZG proof for the grand total, we know that the constant coefficient is not equal to the proof directly, but it's a fraction of the, not equal to the grand total, but it's a fraction of the grand total, and the fraction is exactly, we're dividing by the length of by the size of the polynomial. Yeah, this is the place here.
Okay, since the operation over here is between field numbers and not big ints, uh, can I safely assume that the multiplication over here is elliptic curve scalar multiplication?
Yes, I think you can assume that. But if you're implying any kind of like overflow, then I can elaborate a little bit on that.
Yeah, do you think there's a risk of overflow?
So the
Because if
problem
it's
here
normal
is,
one, I don't think there would be an overflow if it's like normal integers. But if it is doing
yes,
scalar
yes.
multiplication, I don't think so. Yeah.
So here, it would be useful if we had the slides from the first session, but let's try to remember that in that interpolation approach, we uh, we are just taking advantage of that math behind the roots of unity, and
Mm-hmm.
that's why we get the constant coefficient that is related, that is directly proportional to the grand total. And the question here is how does it work, for example, if we have all the values in the polynomial that we are interpolated? What if we have them at the, how to say, at the border of the prime field overflow? Like, what if we just have the balance values that are so high that they are about to overflow? Obviously, if we just sum all of them together, the resulting number will definitely overflow the prime field. But the problem here is that in the circuit itself, we are not summing anything. We don't have a single summing operation in the circuit. We are simply assigning the balances into the polynomials, and we just know that the Hale-2 will interpolate the polynomials for us. So imagine that if the values are high enough to potentially overflow, then it will be very difficult to assess the resulting value of the constant coefficient, because if it, colloquially speaking, if it wraps around the prime, maybe even multiple times, right? You, in the end, you receive some value, and it will probably check out with the proof, with the KZG proof verification, but you will not be able to assess whether this is the correct value, because uh, during the interpolation, during the polynomial construction, uh, it's all done with prime field elements, and there is no overflow per se. It's just like they're just like wrapping around modular the prime. So the problem occurs when we're converting from the prime field into the big int, like the operation that is the inverse of what's going on here is if we obtain the constant coefficient of the polynomial, and we need to convert it to a big U int from the prime field, and also multiplying by the length of the polynomial. So when we're multiplying that constant coefficient by the length of the polynomial, we're still inside the prime field, and we cannot be sure how many times it wraps around inside the prime field before we convert it to the big integer. That's why we had to include the range check into the circuit. We even calculated additionally that with our range of 8 bytes and our prime field, there will never be any kind of overflow, even if we fill the polynomials with maximum values that are just like prime minus 1. So this may be a little bit tricky to wrap your head around, but this is like essentially the problem here is the transition between two worlds, between like the real numbers and the prime field arithmetic. And since it's impossible to detect any kind of overflow inside the prime field because there is no such thing as an overflow, then it is also impossible to detect if any overflow has happened while interpolating the polynomial. And when you're simply converting from the interpolated value of grand sum into the real numbers, you're not able to tell whether this is a valid value or not. That's why if you perform the range check in the circuit additionally, and you simply multiply your maximum possible value by the maximum number of users, and you can see that this resulting value will not overflow the 256 bit of a prime.
Got it. I think this is like a very important aspect, and I'm glad we went over it. I'm curious to know if there are any other crux we should be knowing about.
I'm not sure. Nothing comes to my mind. If any of the colleagues are here, maybe they remember anything else, anything important that I have missed.
This was fantastic, Alex. It's really opened up a lot of interesting ideas as to what to look at. I have some ideas, but I'll probably formulate them better and then share them on Discord later on. But I just want to thank you for all these sessions. They have been fantastic, really.
Thank you.
Yep, couldn't agree more. Do we have any questions? Any final questions? Okay, I'll take that as a no. Thank you, Alex. This was a really good presentation. I sure do have a lot of questions, and as Ali said, I'll formulate it better and share it with you. Thank you for this presentation, and I'll see you guys next Friday. Yeah, thank you.
Thank you. Goodbye.
Thank you. Bye-bye.
Yep.